Hello everyone, welcome to this tutorial. In a previous video, we took a closer look at how to model geometry based on lines. Today we will examine how to work with surfaces. To do this, we will use the building on 57 West Street in New York and recreate its panel structure. The 57 West is a building created by BIG and located in New York. They call its topology a quad scraper, as it is a skyscraper, but it offers its residents the communal space of a courtyard. Its roof surface is panelized in a grid, which is, how we will get to know, not too easy to recreate. We will start by modeling our basic geometry in Rhino. We will begin with our outline, which is a rectangle with the measurements of 150 times 60 meters. And we will also model the outline of our courtyard, which is 110 times 20 meters. But it's of course located in the middle of our outline. To create our roof surface, which is defined as a 4-point surface, we need to find the highest point of the surface somewhere up here. We can do this by drawing a line and then moving its last point 140 meters in the air. Now we can choose the command surface from point, which needs these 4 points to create our surface. Now we will open Grasshopper. The building itself, of course, has this courtyard cut into the roof structure, but as its panelization is continuous, we will first work with this whole surface and then cut in the hole at the end. So what we'll do today is we will examine how exactly we can panelize the surface in different ways, and with this get step by step closer to the actual surface of the 57 West. Of course, we need to reference our geometry in Grasshopper. We can now hide this and work with this geometry only. So we have our geometry, and the first component we will look at is called the isocurve component, which takes a surface and with defined UV points finds its isocurves on it. An isoperimetric curve is a curve on a surface which is defined by constant UV values. The UV values define a surface from 0 to 1. So we have this curve defined by U isocurves in this direction and in V direction, where they go from this divided curve to this curve. In order to do this, we have to reparameterize our reference surface. The reparameterize command will recalculate a geometry's parameters to fit its actual size. So when we define parameters, the space goes from 0 to 1 and not from maybe 0 to 200. So we use this surface as our surface for the isocurve component, and now need to define the UV point on the surface. We can do this by constructing our own point with an x and y coordinate. We won't use this component as an actual point, but we can take the parameters created by it and use it as our UV parameters. How will it look? You will take this as x, this is y coordinate, and we see we have the values 0.555 and 0.777 in this list here. And if we connect it now, Grasshopper takes these values as u and v values and will now choose the corresponding UV parameter. So here we have our u isocurve and our curve in v direction. With this, we can define curves on a surface within its curvature. We can, of course, also find the point on the surface with a command we already know, which is the evaluate surface command. And if we now connect our surface and our corresponding point, we will find the exact point on the surface and use it as well. But these are, of course, only two curves which we could use right now. So we could try to do this, but with a larger list of values. So we use our surface again, blend this out, and start again with the component isocurve. But this time, we wouldn't construct the point by two values, but by a range of values. So we use the component range, which gives us values in a domain from 0 to 1. We could, of course, change this, but as we have a reparametrized surface, it's corresponding to our UV range. And within this domain, we have a number of steps. So right now we have 10 values within the domain from 0 to 1. Would, of course, increase or decrease this count of values. We will do the same for x and y coordinates. And we see that now we already have our surface panelized in a way according to its UV definition. After using these components, we do have the lines on our surface, but we don't have these panels within the surface. It's still one closed surface. There is an easy way to extract these panels, where we will also use the UV definition of our surface, and the component we use is called isotrim. This will now use the UV definition of our surface and divide it in subdomains. So what it will do is it will take this domain of our U and V values and create subdomains in which the panels will be defined. So to create these domains, we will have to construct a two-dimensional domain to construct both the U and V direction in one component. And therefore, we of course need the one-dimensional domains from 1 to 0 for U and V. And if we now take this 2D domain and divide this two-dimensional domain by a certain count in U and V direction, which was basically before the range of numbers in our list. And now we have all these small domains defined, and if we connect it, we see that we divided our surface in a corresponding way to these lines, but instead of the lines, we got the surfaces right here. We can take a look at each subsurface if we just use list item component. So here we don't have a line, but the subsurface itself. This could be useful in many cases, but in our case, if we take a closer look at the building we want to model, we realize that it does not quite fit to the panelization used there. what we can do is to maybe model the floors of the building. We can use the component brep plane intersection, where we cut our brep with a plane defined, in this case by its d vector. And we see that the curves we are getting begin to fit with the floor structure of our building. You may recognize this technique, and you're absolutely right, if we use the command contour. It will do this exact same thing. With a predefined distance between these planes. Just like this. So we would have the lines we need to define the floors of our building. These curves work fine for our horizontal division of the surface. But we still need to find the right curves to divide it vertically. And all these UV components didn't really help. So maybe we just have to define our own curves on this surface. We will start, of course, with the surface itself. And now we will use the component curve on surface. Basically, in a similar way, the isocurves are created. It will create a curve on a surface between 2 points defined by its UV value on this surface. We can, of course, connect our surface, and now we need to define our UV coordinates of the points. We will do it in a similar way as above by constructing the points in a UV space. And as we need all of these points in one list to define our points here, we will take these values and merge them. So we will create out of these two single points in a single list, we will create one list with both points in it. If we want to take a look at them, we can evaluate our surface and see our points right here. If we now connect these UV coordinates with the curve on surface command, we see that we will create a curve through these points on our surface. This curve is, as we saw earlier, defined solely through these start and end points. If we now take a closer look at our building we want to model, we will see that the points all start on these two outer curves of our geometry and all go towards this one line of our surface. So if we now try to create curves from these points on this line to this one line on our surface, we should have the exact division we want for our surface. So where do we start to do this? Well, we'll have to switch back to Rhino for a second and draw a polyline according to the curves we need down here. We already have this single curve up here. If we now reference our curves down here. And up here. We can now simply divide these two curves with the exact amount of segments we want to have. So we'll have this and this. And now what we need to do to connect these points on our surface. In order to do this, we first need to define where the points are lying on our surface in UV direction. The component to use is surface closest point, and we will use these points right here to generate the points on the surface we have here. So we have our UV values defined for the points we have on the surface. Within our curve on surface component, we need the two corresponding UV coordinates in one branch in the list. So what we'll do is we will of course take our UV points up here and merge them into a list. But instead of merging these two lists together in one big list, we will draft our output right here, and with this merge each branch of this data tree and this data tree together. So we now have two items in each branch, like this. And now Grasshopper will connect these two corresponding values within one branch with each other to create the curve we want on our surface. So we will connect it, first of all, of course, with our surface, and then with the UV coordinates as well. And we see two things. First of all, we see that we do have the lines we want to have, but that something in this component failed. And the reason here is, of course, that if we take a closer look again into this list, right here we have 2 points which are the same, so we can't define a curve between them. If we take a look into this list, we see the result of this, which is invalid value here. And to get rid of it, so it won't disturb any further data structure, we will use the component clean tree, which takes our data tree right here and removes our null values or invalid values. And if we take a closer look at the list structure here, we see that we now got rid of our item. We can even remove this empty branch from our data tree and now have only the curves we can see right here. So these are the curves we want to divide our surface. If we would now take these geometries and loft through them as a surface, it would now be defined in a completely different way than the surface we started with, as the UV space would go from, it would stretch from this curve to this curve, and from this curve right here to this curve. How would this look? We can just copy our group up here, down here. And if we now use this surface as our starting surface, we would see exactly how our surface would be defined. These more or less horizontal curves are of course not exactly what we want to do with our building. And we already found the right thing to do, which is our contouring up here. So we will also take this group, copy it right here, and use, of course, our starting surface, which is in this case the same as the surface we are contouring. And with these curves and these curves, we would now have our surface panelized in the way we want to. Of course, just as in the example up here, we only have the curves and not the surface panels. To do this, we will use the command split surface, or in this case surface split, and we will use our surface and our merged curves here and here, flatten the output, connect it, and have now cut our surface with these curves. The important thing to look at here is that our curves are on our surface. If we would have taken any other curves that don't touch or don't lay in our surface completely, this component would have failed, and of course we wouldn't have the panelization we want. But as we defined all these curves on our very surface, what we could do now with these panels is we could combine it with an attractor definition or with a ladybug analysis, which would allow us that we could now design individualized panels to meet the requirements we got from possible analysis. With this tutorial to work with surface geometries in Grasshopper is finished. If you are watching this as part of the course Computational Design Basics at TU Darmstadt, please check Moodle if you have any tasks regarding this tutorial. And if you are watching us on YouTube, of course we hope you enjoyed this video. Leave a like and we hope to see you next time soon.